All right, recording is rolling. It's Thursday, August 11th. Right, so we're in groups today. You got did everybody write their name in the card in the top left corner for groups? Right, so I've got a row set up and a group set up, and well, I've got a team activity for you guys today, but I'll get to that in a few minutes. Right, so follow up from yesterday. Well, you guys don't care about the first couple points, but this hit comment. So this is remember I told you guys there was this flyby in 1682, and that kicked off one reason or another the publication of Principia, which led to physics and the industrial revolution, the modern world, and here we are sitting in air conditioning, looking at prediction, listening to my voice of this ant, all because of physics. So I did go back and fact check myself. How often does Halley's Comet come by? It's about every 75, 76 years. That photographic I saw was from 86. And the next time it's going to fly by, we will all see it in 2061. So yeah, in 2061, put it in your planner, look up at the sky, and we see it fly by. Like, oh yeah, that's the comet that kicked off physics. Speaking of looking at the night sky, we're entering into the Perseid meteor shower, which comes about this time every year. So yeah, next few nights, look at night sky, you might see that. Also, one of the slides I had in the background had a photo of the Hubble Ultra Deep Field, and I did not actually tell you guys the story behind that, but I got a photograph of it right here on the wall. So I don't know, some of you guys might know the story of this picture. You guys know in the last few months, we sent up a telescope called James Webb Telescope. It's like the best telescope we have going on now. And sort of the predecessor to that was the Hubble Space Telescope, which took like a bunch of fantastic pictures. So this went up in the 1990s. You can imagine there are all these different teams of astronomers that want to take photographs of like anything and everything all in space. And this one team of astronomers has this idea, like, hey, what if we just found like some random dark black point in the night sky that, let's say about the size that if you took about like a grain of sand and held it up at arm's length, like how much sky would that cover? Like a little tiny pinprick. Yeah, so maybe something about that big, but just off in the distance, and who knows what we're gonna get. So let's try it out. Now, to know why that was controversial, you have to know something about shutter speed. So let's say it's a really bright day outside, it's noon, maybe some sports event, you're photographing a sports event. Do you want a shutter that lasts, that's open for a long time, or just like just real short? Like 12 o'clock noon, bright, sunny outside. Real short, right? Because if it's open too long, too much light information, it floods the film. And well, what are they do for digital now? Okay, but what if it's really dark outside? What kind of shutter do you want? Yeah, really long exposure time, right? You need lots of light information to make something actually get a real clear photograph. How about if you're taking a picture of like a pinprick at the edge of space? How long do you think you need that shutter open for that picture right there? Really long time. Good call. You are right. How many guys were thinking about 10 days? About 10 days to get that photograph. You think, yeah, like about a week and a half? Yeah. You guys think that the entire time they're taking that photograph, there are a bunch of other astronomers like, oh, we want to put Jupiter, Saturn. You guys think? And they had no idea what they're going to get. They could have just gotten black back, like, oh. But every single one of those bright smudges there is an entire galaxy, which is full of billions of stars. Like the Milky Way galaxy that we're in has, how many stars do you think? Milky Way galaxy?
2 trillion.
A little bit short of that. No, it's kind of a window range, somewhere at least 100 billion. 100 billion is kind of the lower estimate. It seems like maybe up to like 400 billion, somewhere in there. Okay. You guys see this poster? Billion dots on it? Okay. If you had $1 for every dot, you'd be a millionaire. So you'd have to have 100,000 of these posters worth of stars just to represent our own galaxy, and that's a lower boundary estimate. And then there's probably about that for every star in our galaxy. There's another galaxy out there in the observable universe, and that right there, that picture, deep field, that is like the edge of the observable universe. That's like as far as we can see. Now, is there stuff beyond that? Almost certainly yes, but because of how the universe expands and there's this finite speed of light, put two and two together, light beyond anything right there, beyond the edge of the observable universe will just never reach us, so we can't see anything beyond that. Okay. All right, so there you go. There's a fun little story about that deep field. All right, but we're gonna do some graphing today. Keep a pretty good pace here because fit in just what I need to fit in today. All right, so do you guys see some circles on your desk? See some circles? Okay, now this can be a team activity. That's why you guys are groups, so you guys can help each other out. You might have to share some of these around, but there's one with a big circle on it and one page with a bunch of little circles. Okay, so have some paper out. You can use your own paper. You can, if you don't have any paper, then I did pass some blank paper around. I will give you guys points for this, but just how this has been working out today. Tell you what, the way we're going to do this is, if you go ahead and if you want to put this in your notebook and just keep this notes, you can, and I'll just walk around, see how what progress you guys are making. Okay. So up to you. But I do want everybody to write this down on paper. Okay. I'm going to have you guys make a table and then make a few graphs. Okay, so let's start with the table, and then after you guys get the table and all the measured values, then I'll show you guys I want you to analyze that data in graphs. Okay, so this is the table we're doing. Now, 1 table and 3 graphs. You know what? Maybe we should spread this out on different papers. I haven't crammed this all on 1 paper, but maybe I'll make this more spread out. Okay, so if you want to fit 1 table and 3 graphs on 1 paper both sides, or however you want to do it, but maybe I'll try to spread it out a little bit this class. It's a bit more legible. So it looks like I need 5 columns on this table. Okay, so you guys should have rulers. It should be 1 ruler per student out on the desk. There's paper if you need it. So get a nice looking table. You guys got a nice looking table like that. Okay. So there are different circles. Okay. There are 7 circles altogether. Yeah. So go and label them A, B, C. Got a bunch of circles. Okay. Each circle has some radial size. You guys know what radius is? If you forget what radius is, you can help each other out. That's one reason I have you guys in teams today. And also, you guys see how on the printed version of this, I labeled each variable with the corresponding unit, right? Units are really important in physics. I'll recap this stuff with you guys next week too. But what are we measuring radius in? Is it kilograms? Is it seconds? Probably some kind of linear unit, right? And we're going to be using almost exclusively a metric system in this class. What is 1 centimeter? Well, how many centimeters on a ruler? About 30, right? How about this meter stick? Okay. How many centimeters are in 1 meter? 100, right? Because centi is like 100. You guys know 100 cents in the dollar? Right? Metric system. Scale up and down by some power of 10. Okay, so 100 centimeters in a meter. We're going to get circumference. And this is also centimeters. So also a linear unit. I'll show you guys exactly how I want you to do this too, but let's get the table first. Okay. You're gonna have to figure out what is the area of each circle. Now that's gonna be in square centimeters. Right, so like centimeters squared. And then now the last column is a bit more abstract, but it's gonna come together in the end by the end of this class, which is not the radius, but the square of the radius. So this will be a calculated value. That'll be in centimeters squared. It's also an area unit, just like the area of the full circle. You guys get that? Okay. Guys are around on this table. Okay. So we break out these circle. Oh, I should tell you guys too, these circle templates, please do not write on these just because I'm trying to use these for all my classes. Now they might have a couple little marks, maybe students in the past classes that put little dots in the middle that could actually help you out. But yeah, I am trying to use these for all my classes. Right. So got these different templates, these different circles. Okay. You guys can share these around, measure them. Okay. So first one, radius. If I need some radial side, let me do the tiny circle because that one's probably pretty straightforward, right? So I need to find the middle of this, probably right. There's the middle. Break out my ruler. Yeah, what is the radius of this thing? I'm gonna say about 1.1 centimeters, I think is pretty close. 1.1 centimeters. Okay. If you measure it yourself and get like 1.2, that's fine. You can write 1.2. Everybody's measurements might be a little different. Right? There's always a little bit of error in the tools you're using, the way you're interpreting. It's part of science. Okay. It's all empirical data, right? Okay, now circumference. Now here's what I'm gonna have you guys do for circumference. You guys see some string and scissors on your desk? You guys see that? String scissors? So you can cut little lengths of string. It's got one here. And so since I'm focusing on the little guy, like this, you take the string and just wind the string all the way around the circle. Okay, more string than I need. Okay. Okay. The bigger circles are actually easier to do this with. Okay. All right, I'm trying to match the string up with the ink of that circle. It's like right there, right there. So cut off right there, right? And then if I pull that out, that would represent the circumference of the circle, wouldn't it? Ah, all right. So pull up a ruler. Let's see, how many centimeters is this? That looks like 7.1. I'll call it 7.1. Okay. If you do it yourself, you get a slightly different number. That's fine. That's what I got. Okay. Good so far? Okay, now what I want you to do for area is, well, this is where that grid comes in. I want you guys to count how many squares are here. Now, you can confirm this too if you want to, but each square is 1 centimeter by 1 centimeter. So there's 1 centimeter wide. Maybe I'm slightly lying to you guys. Looks like my printer made each one tiny bit bigger than this. Okay, well, pretty close though. About 1 by 1 centimeter. That means each tile is like 1 square centimeter. Right? So basically, how many tiles are in each one of these circles? Well, let's focus on the little guy. I do see it's kind of covering 4, except that a lot of those tiles are like outside the circle, so I can't really count that area. Hey, what if I do this? What if I go like 1, 2, 3 tiles, and then like chop off this corner, chop off this corner, chop off this corner that are outside the circle, and take that area, imagine it's like Play-Doh or something, right? And then wouldn't that basically fill this void pretty close to? Maybe not exactly, but that's probably a pretty good estimate. Do you guys think this circle is probably pretty close to 3 tiles worth of area? 3 tiles, right? So that's my best estimate. I'm just going to write 3. Right? I'm only writing 1 digit there because I don't really have much precision beyond that, but it's pretty close to 3 tiles. Then this very last column, the square of the radius. Now this is the one that you can pick up a calculator for, right? So pick up a calculator, just take your radius, 1.1 in this case, and square it. Now remember, look, the unit also gets squared, doesn't it? Centimeters squared also becomes square centimeters. Get that? So the number on my screen says 1.21. Now, if you're maybe a stickler about significant figures, might say, especially if you come from chemistry, they're a lot stricter on sig figs than in physics. Okay. Might say, well, do you really know that this last one is really there? Maybe you can say 1.2 is as much as you can say, which is probably true. But I don't use it, write 1.2 or 1.21, kind of loose with the digits in this class. So, okay. Right. Any question about what you're doing? Right. So help each other out. Get as many circles as you can. I'll give you guys some time and walk around and see how you guys are doing and help you out. And in the meantime, I'm going to pause this recording and pause. And recording is resumed. All right, so I've been walking around class. You guys have been doing a great job on this so far. So great teamwork, great measurements. If you have at least 5 circles, then you're good. And this is going to work. I know you gave guys 7. If you have at least 5. If you're a couple short, you want to steal one of these. This is data from Gina, Kaylin, and Alexis are sharing with you guys. So we're going to see. We're going to see how this works out. All right. Let's make some graphs. All right. Now, if you want to just on the same paper, that's fine. I'm going to do new paper just so it's blown up bigger and looks more legible. The first graph we're going to do, let's do circumference versus radius. Yeah, right. Right, so make a set of axes. Right. Now I'll label that title. Exactly what it said: circumference versus radius. Okay. Now that title tells you which variable goes on which axis. Do you guys remember how it works? Is it x versus y or y versus x? It's like y versus x. You guys remember that? Okay. Which means that what goes on the vertical? Circumference or radius? Circumference. So go ahead and label the vertical axis circumference. If you just want to do capital C, that's fine. Okay. And then you have to label the unit so that whoever's reading this graph can very quickly interpret, is that seconds? Is that kilograms? Oh, we're looking at meters, or sorry, centimeters. Okay, centimeters. Okay. So variable unit. You guys get it? Variable unit. Okay, and then on the horizontal axis, right, radius, and that's also going to be in centimeters. So centimeters and centimeters. Okay. Yep. Okay. Now I need to scale each axis. So what's the biggest circumference? This one goes up to say 36, and then okay. So it needs to because at least that big. How about this? How about 10, 20, 30, 40? That'll work, right? So it started at 0, of course. 0, 10, 20, 30, 40. Now those numbers have units attached to them, but that's already taken care of. We did that by writing centimeters. So that's 10 centimeters, 20 centimeters, right? You guys go. How about radius? Looks like according to this table, now you might have measured the big circle. Maybe you have bigger numbers, and that's perfectly fine. But my big swan here is 5.4. So how about this? 1, 2, 3, 4, 5, 6. That should cover all the radial sizes, right? So 0, 1, 2, 3, 4, 5, and then 6 would be here. Okay, that's radius measured in centimeters. So all those numbers are also centimeters. Guess that. Okay. Do you guys see how we're about to plot a bunch of Cartesian points, right? Like x, y, right? So over radius up circumference, that's like over x up y. So x, y, x, y, x, y, x, y, x, y. You guys see that? Okay. So let's try it out. Of course, if you have different numbers than I do, then it's perfectly fine. Go ahead and plot your data. But our graph should look kind of the same. Hey, I wonder what this graph is going to look like. Oh, so over 1.1 up 7.1. 1.1, 7.1, right here. Over 1.7 up 11.5. See 1.7, 11.5. Over 2.2 up 14.5. Over 3.6 up 24.5. Over 5.4 up 36. 36. That's about there. 5.4 is about there. Ah. Yeah, this is gonna work. Then so take a quick trip around the room, make sure you guys are doing all right. Yeah. All right, I see axes labeled, title, axes, labeled and scaled. You guys got a bunch of points. All right, I think this is looking good. Yeah, you guys are where you need to be. All right, so now we need to make a curve of best fit. Now, a curve might be a straight line, or it might be maybe like a parabola. Right? Hey, what do you guys think is like the curve of best fit? Do you think it's a straight line? Straight line? Yeah, looks pretty good, doesn't it? Pretty well straight line. If it was 0 radius, it would be 0 circumference. So you could sort of extrapolate through the origin. Should look about like that. Okay, maybe I'll dash the part that's extrapolated through the origin. Say, well, that would be true. If it's 0, 0, kind of could be a point, right? Hey, what is the equation, like the algebra form of an equation for a straight line? Y equals what? Y equals mx plus b, right? In fact, if it is through the origin, then what is the b value in y equals mx plus b? 0, right? The plus b just moves line up, or minus b takes it down, right? Up or down, right? So if it goes through the origin like this one does, isn't it just like kind of like y equals mx? Huh. Instead of y, it's circumference. Instead of x, it's radius. See how we're taking this abstract algebra equation and actually applying it to like actual like measured variables? So if only we had the slope of this line. You guys remember slope is rise over run? Here, put a little stick figure on here in case this helps. Right. Some of you guys made a refresher. If this guy's walking left to right up a mountain, okay, if it's a 0 slope mountain, like the floor that we're actually on in this classroom, then that would be like 0 slope, right? So 0 rise per whatever unit run. Okay. If he's going up a cliff, then it's like infinite rise per every unit run. Okay, so the larger the slope, the steeper the climb of the mountain, right? Huh. I bet if we pick 2 points that and then find the rise over run between those 2 points, they would get the slope. Okay. I'm going to pick this point and this point. Right, no, let's do this point, this point. Oh, looks like runs parallel to the line of best fit. Guess that. Okay. So, I wonder what is the rise between these 2 points, and what's the run? And then if we just divide those, rise over run, that would tells the slope. Right. Let me pop in those coordinates. So here's my coordinates page. 5.436 was this one. 5.4 comma 36. And then this one was 1.1, 7.1. 1.1, 7.1. Okay, so I got my coordinates. Okay. So the rise, wouldn't that be, see this y value 36, this y value 7.1, whatever 36 minus 7.1 is. Right, so this rise looks like 28.9. And of course, that's centimeters. All these numbers are centimeters on this, right? And what's the run? And try this with your data too. I have slightly different points. Well, it goes up to 5.4 is the biggest x coordinate, and the smallest one's 1.1. So this looks like 4.3. So 4.3 is the run. So there's the rise, there's the run. Okay. Okay, so the slope, which is rise over run, I'm doing, here's how much it rises in centimeters. Here's how much, here's the run, also in centimeters. Right. In physics, really all numbers have units attached to them. Centimeters are going to cancel out anyway because they divide out. Right? But what is 28.9 divided by 4.3? And that is 6.7. Okay, so to bring this all together, let's write an equation for this line. I'm going to put it in y equals mx plus b form. But instead of y and x, so the plus b is just 0. Right? Instead of y, it's circumference. So I'll say circumference equals. Here's the equation. And then instead of x, it's radius. So something times the radius. Okay. And guys, what number goes right here? 6.7. Okay. Okay. So do you guys see how now you have a graph and so that in an equation that gives you it has predictive powers, right? So you can have any circle of radius any size, and if you scale it up by a factor of 6.7, you should be able to predict pretty well what the circumference is. You guys get it? Except I bet so many guys are looking at this saying, hang on a minute, I've seen this before. I taught it in elementary school, and I don't think that's exactly right. I don't think this number should actually be 6.7 in the textbook. What's the textbook value? What number should actually go here? You guys say 2 pi? What is 2 pi? 2 pi, 6.28. This number should actually be 6.28. You guys remember a little formula called circumference equals 2 pi r? That's basically what this is, isn't it? You guys just found this out empirically, with empirically meaning like you actually measured the data, right? But it's taking the form y equals mx, where m represents the slope in this context, and gets used a lot in class. But really, the ideal value formula should have been circumference equals 2 pi r, and we got pretty close because 6.7 is pretty close to 6.28. So, okay, you guys get so far? Okay, and we're good on your page 2. Right, I want to do 2 more graphs. Okay, you guys ready for our next 2 graphs? Okay, we got just enough time to. Okay. You know what? Maybe I will do these graphs side by side. So I'm going to kind of squeeze these graphs together, but I'll be right. If you want to do one per page, or if you're still using the same page, whatever. Right. I want to do area versus radius. And then the last one we're going to do is going to be area versus radius squared, which is kind of an abstract idea, but you guys will see by the end of class of where this is going. Okay. So go ahead and make a couple of sets of axes. You guys know each vertical axis is going to be the area. We'll go ahead and label that A. Now that's going to be in square centimeters. So label your unit, because all numbers in physics have an associated unit. Okay. That's true for each of these. Area is in square centimeters. Okay. And then see the graph that we're about to do has radius measured in centimeters. And the last graph we're going to do today is going to be the square of that radius measured in square centimeters. Okay. So I have 2 graphs lined up. Each has a title. Each has axes that are labeled with the units. Okay, now I need to scale each one. So if I go back to this table of data, I'm just going to pick different columns and treat these as XY coordinates. Okay. So area versus radius, that's these two columns. So you guys see it's gonna be like x, y, x, y, x, y, x, y, x, y. You guys see that? Okay. So my biggest x value is 5.4, just like before. So my biggest y value is now about 101. So radius, go 1, 2, 3, 4, 5, 6. So 0, say 1, 2, 3, 4, 5, 6. Those are all in centimeters. And then the area goes up to 101. So let's go, how about this? 20, 40, 60, 80, 100, 120. That should cover all of my data. 0, 20, 40, 60, 80, 100, and then 120. And those would be square centimeters, but that unit is already embedded in the axis. Now I need to plot all these points. So my first coordinate is over 1.1 up 3. So 1.13. Over 1.7 up 8. 1.7, 8. Over 2.2 up 14. 2.2, 14. 3.6, 33. 3.6, 33. 5.4, 101. So over 5.4 up 101. Now, again, you might have your own individual data, but your graph should kind of take that shape. Is that still a straight line? No. Do you guys think if it was 0 radius, that should extrapolate to 0 area also? So maybe we've got this little extrapolation part. What shape basically do you think that is right there? Might start with a P. Parabola. You guys think of a parabola? Okay. Which, by the way, is not exponential. Exponential is like 2 to the x. This is like x to the 2, which is a different thing. Okay. So yeah, maybe some form of a parabola, right? Well, let's see if we can kind of put this together in a equation. Area equals something. Something times r squared, right? Wouldn't that be the case? Area equals something times r squared, because a parabola is something like y equals something x squared. Okay. Hey, do you guys remember maybe a formula from a math textbook? What ideally should go here? Pi. It should be pi, shouldn't it? Okay. Now this is I'll label this ideal. That's not based on empirical data like that you just measured. This is from a textbook. Right? Area equals pi r squared. So maybe we're getting the question like, how curvy is this parabola? And the answer is like pi, right? You see that? Right? If you change out pi, you might stretch or squash, right? So last thing we're going to do, last graph we're putting together, is to actually take the same data and just linearize it. Do you guys see this form? This could take the form y equals mx. That's what we're about to do here. We're going to go, here, let's write it again. Area equals something r squared. Except I'm going to leave a blank there where the pi used to be. You guys know ideally this should be pi. And we call this y equals, mx. But do you guys see how instead of x being one of the measured variables, it's kind of this abstract idea of the square of the radius, right? I guess you could take the radius, square it, make a nice little square shape, right? Be like hanging off the circle. You guys got that? Okay. And we're going to see what empirically actually would go here. And we're going to figure that out by linearizing this data. All right, so last graph, let's put this together. So we've got areas. Okay, well, actually, I have the exact same area axis that I did before. So I'll scale it exactly the same as before. So 20, 40, 60, 80, 100, 120. So 0, 20, 40, 60, 80, 100, 120. Okay. But the horizontal axis is going to be different. It's not radius, it's the square of the radius. So we're gonna like this here's my x values, here's my y values. So x, y, x, y, x, y, x, y, x, y. You guys see that? Okay, so my x values go up to 29 point something is the biggest one. So how about 30? About 5, 10, 15, 20, 25, 30. And those are square centimeters. 0, 5, 10, 15, 20, 25, 30. Okay. Okay. Now I'm going to plot these coordinates. 1.21, 3. 1.213. Ooh, that's real tiny here. It's like there. 2.898. It's right there. 4.8414. 12.9633. 12.9633. And 29,101. So 29 something, 101. Ah, now look at those points. Do those points line up in a straight line? Pretty close, isn't it? Pretty close to a straight line right there. Okay. One dot below, one dot above, line of best fit. And that is a linear relationship. Now remember, it's not a linear relationship between the area and the radius. No, that was a parabola. But area versus radius squared actually is linear, which it should be because you guys know the form. It's gonna be ideally it should be area is pi r squared, but we're about to figure out how close that is. Let's do rise over run. You know what? How about this? I'm gonna pick between these. How about this? This very last point and this very first point. So this rise versus this run. Now, do you guys see how if I pick these 2 points, I should get a value that's a little bit bigger than the line of best fit for the slope, right? So maybe this would be a little bit of an overestimate, right? Maybe I should get a number a little bit bigger than pi, but we're going to find out. Okay? So what was the squaring again? It's like 29 over 101 up. And this very first point was 1.213. So 1.21 comma 3. Okay. So that's that point right there. It's this point right here. Okay. So what's the rise? Let's subtract the y values. So 101 minus 3. That's a y. That's a change of 98. Okay. And this was actually it was 29.16 was the x coordinate. Subtract the 1.21. Right, and this is a run of 27.95. There's my rise. There's my run. Okay, let's do rise over run. So the slope of this linearized graph is, there's my rise, there's my run, what is 98 over 27.95? I'm looking at 3.5. So I'm getting the equation for this empirical data is area is 3.5 times r squared. But remember, you guys know. Let me see, you guys are following, or you guys remember this. This number ideally should not be 3.5. The textbook value should be what? Pi, at 3.14. So actually, it's not too far off. It's pretty close, isn't it? In fact, I was even guessing it was going to be a slightly overestimate because if you take this point, it's a little bit above the line of best fit. Yeah, you guys see that? All right, there you go. So we're going to do plenty of labs throughout the year where you guys are going to get to see this linearization technique, but of course it'll be physics variables. All right, yeah, you guys did a great job on that. So I will give you guys credit for doing that because I walked around and saw you guys do that. You guys did a good job. But yeah, be onto that page and yeah, become familiar with the idea because that's a pretty good tool to have in your back pocket.